In this video, we are going to discuss an important transformation property of multivariate normal. So our theorem starts like this. We have y, which is a multivariate normal random vector with some mu and sigma. Now, what I do is I apply an affine transform to it. By this I mean I multiply y by some matrix B. It must be of appropriate order so that the multiplication is defined, and then I add a fixed vector. So here B can be any matrix, fixed matrix. C is any fixed vector. B I have taken n cross m. N can be any natural number. C is n cross 1. As a result, you get a new random vector which I have denoted Z. Remember, Z resides in n-dimensional space while y resides in m-dimensional space. Now we are going to claim that if y has multivariate normal distribution, then Z must also have multivariate normal distribution. Since it is n-dimensional, I have to use n as a subscript. Now I will write down the mean, I mean the first parameter and the second parameter. Now observe how I am doing it. I am taking the first parameter here, applying the same transformation to it. So it is B mu plus C. In case of sigma, I shall pre-multiply with B as I have done in case of Z. Then I will post-multiply by B transpose, which is kind of natural because I need this to be symmetric after all. So it is B sigma B transpose. Be very careful. It is a natural mistake to replace it with B prime sigma B. This in general may even not be defined. So it is not this. Now you can do this proof either using characteristic function or directly from definition. We shall prove it directly from definition of multivariate normal. To apply the definition, we start by taking a square root of sigma, so to speak. So we write it as A into A transpose. We know that any A would do. At least one such A must exist because capital sigma is non-negative definite. I just take any such A. Now you take a random vector x, normal 0 vector I, which is just another way of saying that all the components of my x vector are IID, normal 0, 1. So I am just writing it in one line. And then I know that y has the same distribution as A times x plus mu. That is exactly the definition that we had given, which combines both the singular as well as the non-singular case. Now, what I am doing is I am obtaining Z, multiplying this B and adding C. So, Z will have the same distribution as, I am writing this in place of Y, I will pre-multiply by B and add a C. And what is that? That is BAX plus B mu plus C. This part is random, this part is fixed. Now again I shall apply my definition. Because this is based on normal 0, 1, all the components are IID. Now my definition tells me that Z has a normal distribution with appropriate dimension, and this fellow plays the role of the first parameter. That's just the definition. And this times its transpose plays the role of the second parameter, BA, and times BA transpose, which is A transpose B transpose. Now once you remember that sigma is AA transpose, you just replace this with sigma and you are getting exactly what you were supposed to prove. The first corollary goes like this. Suppose I give you lots of random variables jointly distributed as a high dimensional normal. In this case, normal with dimension 5, and you are given 5 cross 1 mean vector, 5 cross 1 mu vector, and a 5 cross 5 sigma matrix. Now suppose someone says that out of all these things, these are lots of variables. Typically in statistics you have collected data on lots of variables. You are interested in only a few of them. In a particular study, you care about only say x1 and x4. You want the distribution of x1 and x4 alone. In that case, that is very easily obtained. You just consider the corresponding things here, and similarly the corresponding submatrix. So first and fourth rows as well as first and fourth columns. So it will be bivariate normal 2 with mean this and this, and covariance matrix this, and this. And why does it follow from that theorem that we did? It is because you can think of having x1 to x4 extracted from the full vector by pre-multiplication of this matrix. So this plays the role of B in the theorem, and I am not adding anything, so I am adding 0 vector. So just apply the theorem and you will get this interesting result. The second corollary starts with a multivariate normal random vector where I assume, additional to the fact that sigma is n and d, I also assume that it is non-singular. In that case, when you write sigma as A into A transpose, which you can always do because it is non-negative definite, you are also guaranteed that this A is non-singular, because if A is singular, product of singular matrix can never be non-singular, so this must be a non-singular matrix as well. Now we shall apply a special transform to X. It is subtracting the subtracting the mu vector and then multiplying from the left by A inverse. So this is also an n-dimensional random vector, and using our theorem, this is nothing but an affine transform. I am multiplying the matrix by a fixed matrix from the left, and I am adding a vector, fixed vector. This will turn out to be normal 0 and I. So whatever multivariate normal you start with, as long as this capital sigma is non-singular, here is a transform which will let you arrive at the normal 0I thing. Now this is comparable with the univariate result, that if X has normal mu sigma square distribution where sigma square is strictly positive, then X minus mu by sigma has normal 0, 1. So this condition, strictly positive, has its multivariate analog, capital sigma is non-singular, and just like the univariate case, this is also called standardization. In this exercise, I give you a bivariate normal thing. I have given you the mu and capital sigma. Your job is to find distribution of this thing. So you have to express it as an affine transform of capital X, and here is the result in a compact format that we have discussed. So here is your normal thing that you start with. If you pre-multiply by an B and add C, then the mean change, the mu vector changes in this way and the sigma matrix changes in that way. So use this result to solve this problem.